So the question is, can a large language model actually help us to support in autonomous driving decision making? We answer this question with yes, and today we present our research paper DualAD, dual layer planning for reasoning and autonomous driving, which was presented at this year's IROS 2025 conference. My name is Johannes Beetz and I'm presenting on behalf of the TUM Autonomous Vehicle Systems Lab. When we look at autonomous driving tasks, you see actually that driving with an autonomous car can be quite difficult. What you see here in this image is a real-world situation which demands high-level reasoning. You see here cars are on the same road as ours, humans walking over the road where they shouldn't be, and you see there is actually no road. So the question arises, how does an autonomous vehicle operate exactly in these environments? Today, this is quite difficult because there's multiple challenges that an autonomous vehicle needs to overcome. First of all, we need software that adapts the vehicle to the situation, to the use case, and to the vehicle setup. Number two, we need to drive an unstructured environment with high prediction uncertainty and therefore solve the complexity problem. And number three, we ultimately need to overcome rule-based systems and expert-based tuning data. We need to learn from data and generalize with our autonomous systems much more as before. We are tackling this problem by having a look in how humans actually drive a car. When we figured out from the state of the art that when humans drive a car and drive in simple scenarios, it is less cognitive demanding for them. They basically drive literally on autopilot. But now, when it comes to more complex scenarios, it is cognitively much more demanding. There are no more simple causal relationships than in simple scenarios. They need more attention and specific high-level reasoning that intervenes with your current driving situation. Based on this learning, we said that we need a special autonomous driving framework which we call dual layer. In this DualAD planner, we combine large language models with a classical motion planner and imitate human cognitive processes while driving. With this, we are having the goal to drive much safer and more reliable in complex scenarios. How does it work? In our DualAD framework, we are inspired by humans driving and set up two different layers. First of all, we need to capture the driving scenario itself. Here, we are inputting the perception results, which includes the vehicle's position, heading, speed, camera information, and other obstacles. Then we move into the DualAD part. The bottom layer of DualAD is a classical motion planner, rule-based, frame-based motion planner, which is responsible for handling regular driving tasks, such as following the road and calculating a trajectory that is safe and reliable. But now comes the upper layer, which is novel here. Here we introduce a special text encoder that converts the driving scenario into descriptive text, which will be fed into a large language model for reasoning. Now this reasoning layer steps in when it's necessary, when high-level reasoning is needed, and when we have special situations, for example, potential dangerous situations. Ultimately, the reasoning output will adjust the driving speed. For instance, if the rule-based planner chooses a speed that might lead to a collision. Large language model now uses its reasoning abilities and adjusts the speed to ensure safety. We see that kind of result exactly in this situation. On the top part, you see the classical motion planner, which is using a frame-based system, which is driving on the road and doing an overtaking maneuver. In frame number 100, we see that a collision occurs. This is classic for normal motion planners because they cannot adapt to certainty of a situation. Now in below, you see our new DualAD planner, which has the high-level reasoning of the large language model and our motion planner combined. Now our car depicts not only the road information, but that there are multiple other vehicles and therefore our car slows down and will not lead to a collision in frame 100. This scenario depicts already the successfulness of this idea. We then tested it on the new scenes benchmark and could figure out that we can heavily improve the classical motion planner with this high-level reasoning framework. The rule-based motion planner is heavily improved because our DualAD now scores higher than the related classical motion planner in thousands of scenarios. This is due to the fact that this high-level reasoning creates now a more safer driving, slows down the vehicle in dangerous situations, and can create the reasoning if a situation is uncertain. Of course, large language models are growing and still grow over the last couple of years. We already tested out several GPT-4s, 4o, for Flash, and we also integrated the no LLM, and we could see that the system's performance scales with stronger large language models. That means for you, if you have a new large language model, for example, ChatGPT 5 or 5o, you will see a more successful reasoning and therefore you can intervene better. This paper was presented at IROS 2025. That's it from our side. Thanks a lot for watching. If you like to dive deeper, you can check out the links on the left and you will find the preprint of our paper, the source code on GitHub, and more information about our team and our projects and the lab website. Thank you very much for watching and best wishes from the Autonomous Vehicle Systems Lab at TUM.